Hey everyone, I'm James. Welcome to another episode of Foul Suits. Today we're going to look at eclipses. Eclipses hold a special place in my nerdy heart because in 2017 I had the amazing opportunity to view the Great American Eclipse from the summit of Mount Bora, the highest point in Idaho, from an elevation of 12,662 feet. This is a 360-degree panorama I shot during totality. It's a composite of nearly 30 different frames shot over 2 minutes. For about 2.5 minutes, it was dark all the way to the horizon in every direction, where it looked like a sunrise in every direction. It was absolutely one of the most amazing things I've ever seen, and I will never forget it. For a full write-up of my eclipse experience, I'll put a link to my blog post in the description below. This will actually be a 2-part episode. Today we'll examine why the moon has a shadow smaller than itself, but also why it doesn't, and how this relates to the sun's light supposedly hitting the Earth in parallel beams. And then in the next episode, we'll examine the movement of an eclipse and why it moves across the Earth the way it does. These are both points of contention with science deniers, but we'll start with the first one, the size, shape, and pattern of an eclipse. It might be somewhat understandable how people can be confused by this. We're normally told that light from the sun hits the Earth in a parallel fashion, such in these illustrations. But then we also have diagrams of eclipses showing sunbeams traveling at really dramatic angles and crisscrossing each other, like these. This one was the subject of a rather irate YouTuber named Mr. Thrive and Survive. I put the link to his video in the description. He gets himself all in a tizzy over it. This one I found in a video with several people, including a NASA scientist, trying to explain eclipses. I'll put the link in the description. One commenter on the video said, "It's worth watching just for the diagrams. The first one was the best. Absolutely priceless. 23 seconds in, the way the sun has been brought really close to the Earth to justify the 70-mile shadow theory, I nearly wet myself laughing. For that diagram to be believed as accurate would mean that we would view the sun as absolutely massive and a total eclipse would be impossible. The sun would almost fill the entire sky. How can people take this stuff seriously?" I'll agree with him on one thing. The illustration isn't accurate. It's not even close. But that's not proof that eclipses are fake or that the globe model explanation is wrong. Another commenter said, "Why are the solar rays leaving the surface of the sun from 2 arbitrary points on the sun's surface?" This guy is at least asking an honest question. These are the types of people that I'm hoping will get something out of these videos. So there are 3 really important things to keep in mind when you see these illustrations, or really any illustrations like this. 1, they are not to scale. 2, they are not to scale. And 3, they are not to scale. Not even a little bit. In order to show what's happening with an eclipse, these illustrations are by necessity grossly out of scale. They act merely to show the concept of what's happening, the basic layout, and they don't reflect real-life sizes, distances, or angles. Them not being accurate in scale does not mean that what they represent is fake. So to help illustrate the concept, I've again set up my Earth-Moon system that I used in the Discover satellite video. They're scaled distance to each other and a scaled distance away from each other. Now, for an eclipse, I also need a sun. But to do that at scale, it would have to have the diameter of 2.5 city buses and be 3.5 kilometers away. Not very practical. So I'm going to have to scale down my sun. So instead of it being really large and far away, it's going to be really close and much smaller. So this will be my sun. This is one of my studio strobes with a simple reflector cone on it. So the sun is not a single point light source. It has width and height. We can see this. So every point on the sun emits light in every direction. That's why you can see every part of the sun from anywhere on Earth, from the center right out to the circumference. Seems like a simple concept, but it seems like there's a lot of flat earthers and science deniers who don't get that. It'll be the same with my strobe. Light from the strobe bulb will go out in every direction and be bounced from every spot in the cone in every direction toward my Earth-Moon system. From direct observation, we can see that the sun and the moon have the same relative size in the sky. Hopefully we all agree on that. So I moved my reflector cone so that it was the same relative size as the moon when looking from my globe. So that distance was 20.7 meters, and then I moved it back a further half meter to 21.2 meters because I want to exaggerate the size of the umbra on the globe. So I have my globe positioned so that the eclipse will occur over the Central Pacific because it'll stand out better against the solid blue. So let's take a look. You can clearly see the umbra near the equator south-southeast of the Hawaiian Islands. There's also a penumbra, but it's fairly faint. I have a technique in Photoshop I can use to clearly show the entire penumbra, and to do that I'll also need a picture of the globe with no eclipse on it. In Photoshop, I overlay the one with an eclipse on top of one without an eclipse. Then on the eclipse layer, I select a blend mode called Difference. What this will do is any pixels that are identical will turn black, and any pixels that are different will keep their original color and density by degrees of difference. The more the same they are, the blacker they'll get. So let's see what that looks like. So now we can more clearly see the umbra and the full extent of the penumbra. So there it is. An actual eclipse using real models to scale with no misleading illustrations. So now the question is, why do we get these two regions of an eclipse when the sun's light is supposed to be hitting the Earth in parallel rays? First, let's look at the sun and the Earth without the moon in the way. Like I said before, light comes off every point on the sun at every angle. So there is light from near the sun's north pole hitting near the Earth's north and south poles and every point in between. Light from near the sun's south pole is also hitting near the Earth's north and south poles and every point in between. Light from the sun's equator is hitting the Earth's north and south poles and every point in between, etc., etc., until we get every point on the sun evenly lighting every point on the Earth. So far, so good. Now let's see what happens when we throw the moon in there and play that same sequence again. It will block some of the sun's rays from hitting some of the Earth's surface, creating the partially lit penumbra. It'll also block all the sun's rays from hitting one part of the Earth, the completely dark umbra. And areas outside the penumbra are still fully lit. But if we look at the lines and rather big angles going on in this illustration, they are obviously nowhere near parallel. As I mentioned before, illustrations like this are ridiculously out of scale. They're like that for a reason, and that's a very important factor to remember. In this illustration, light coming from a spot on the sun's equator and spreading out to hit every spot on the Earth has a spread of 16.9 degrees and angles of 81.5 degrees at the poles. But if you look at it in scale, with the two sides of that same angle stretched out over 145.7 million kilometers, now the angle of spread starting from the sun's equator and ending at the diameter of the Earth is only 0.00501 degrees, with the two lines being indistinguishable. If we zoom back into the Earth, the angles at the extreme of the spread at the polar regions are each 89.997 degrees. Nearly right angles, and for all intents and purposes, the two lines are parallel. Repeat that for light off every spot on the sun, and you get very similar results. So you can start to see how making a scale-accurate illustration of how an eclipse works that shows the sun, Earth, and moon, and gets the concept across can be problematic at best. So let's go back to our Earth-Moon system. I'll cover the moon with a green dot so it stands out better. Let's say there is an eclipse hitting North America. That means the umbra cone would look something like this. and the penumbra region like this. Over enough distance, you can start to see the very shallow angles. But if you look at shorter segments, the lines are essentially parallel. So hopefully this helped you understand why eclipse shadows are shaped the way they are. The illustrations that are usually used to explain them are by necessity nowhere near scale, and if they were, they wouldn't convey the concept nearly as well. So that'll wrap it up for this episode. In the next episode, we'll take a look at eclipse movements and why they move from west to east and not the other way around. So if you like this video, hit the like, subscribe, and thanks for watching.